Hello everyone, welcome back to my channel. Today we're going to go over this problem of fluid mechanics. Fruit-shaped body is rotating at a constant angular speed of 100 rotations per minute in a container filled with SAE 10W oil at 20 degrees Celsius as shown in the figure. If the thickness of the oil film on all sides is 1.2 millimeter, determine the power required to maintain this motion. So basically, let's first come up with a free body diagram of this object. So the object looks something like this, and there is going to be a torque on both the top and bottom faces due to shear stresses uh, from the viscosity of the fluid. So there's actually going to be um, torque on the top and bottom. And how we can represent this is we can draw all the faces. And all of this has an associated torque. And the sides also has an associated torque with it. So the sides we can draw as such. And it has, this is the lateral view. And it also has a torque associated with it. And why torque is important to consider is because the power required to drive the object will be the dot product of the torque acting on the object T with angular velocity omega. So in short, power is equal to torque times omega. And yeah. As we just mentioned, the torque is going to come um, from because there will be a torque acting on the object as a result of viscous forces applied by the oil on the top, bottom, and sides of the object. And the viscous torque acting on the top surface of the object and bottom of surface of the object can be calculated first, since those can be calculated in a similar fashion. Basically, this is for the top view, and this is for the bottom view. And our goal is to sum the torque on both of these surfaces. So the top has a radius of 4 cm, and the bottom has a radius of 2 cm. And we're going to have to take differential element dA later on. So let's call this dA. And basically, the tangential speed is equal to the tangential speed u is equal to omega times w in general form. These are just general forms, so they're not equal, but we're just using the same symbols for both to denote um, their rotational speed and its relation to the tangential speed. Um, Now let's find how to express torque as a differential torque. Because we have to sum the total torque over this space. So we have to find what the expression for a small unit of torque is. So basically, um, in this case, we use the relationship for shear stress tau is equal to mu times du over dy, where mu is the dynamic viscosity of the fluid. And u is the tangential speed. So tau is equal to the shear stress, and this is the general expression for shear stress for a Newtonian fluid. And SAE, I believe, is a Newtonian fluid. So basically, SAE 10W oil is not really a Newtonian fluid, but the Newtonian equation for shear stress is generally a good approximation, but with some key considerations. For many common applications, it can be treated as a Newtonian fluid. However, for specialized or high shear conditions, its behavior is more accurately described as non-Newtonian. When the Newtonian model applies, for a fluid to be considered Newtonian, its viscosity must remain constant regardless of the shear rate, the speed at which the fluid is sheared or stirred. For basic lubricating applications, SAE 10W oil behaves in this way, and Newton's law of viscosity can be applied. So when the Newton model is insufficient, modern motor oils like SAE 10W are not simple base oils but contain complex polymer additives that improve their performance across a range of temperatures. These additives can cause the oil's viscosity to change under certain conditions, making its behavior non-Newtonian. I'm guessing that the temperature causes it to be Newtonian in this case. So for single grade oils like SAE 10W at consistent temperature 20 degrees C, you can use the Newtonian fluid equation for shear stress. So the W indicates a specific low temperature viscosity, but at a constant 20 degrees Celsius, the fluid behaves as a Newtonian fluid. And this means that for SAE 10W oil at a constant 20 degrees Celsius, the viscosity will remain constant regardless of the shear rate applied. And thus, the Newtonian equation is an accurate and appropriate model to use in this scenario. So, yes, we can use this equation for shear stress. And we can express it as mu times du over dy. So what is du? Well, du is going to be varying differentially. So we're gonna have to integrate it, but it's omega times w, omega times r. And r is basically this portion over here from when the radius is 0 all to the when the radius is at maximum. We're gonna have to sum the total torque on the face. And what about the dy? Yes, so basically we can divide this surface into differential areas. We can also do it this way. So where the differential area is actually this whole ring over here. And similarly for here, we can also use that as our differential element. And this differential element is going to have a thickness of, let's call it dr, or a very small radius. So basically, this ring, it has a, this is dr. And the radius is going to be the location of this differential area from the center. So this is what our area is. Because every ring is going to have the same associated rotational rotational motion, but it's going to be at a different R from the center of the face. And what is dA going to be? Well, dA is going to be equal to the circumference of this ring multiplied by the thickness, which is dr. The circumference of this ring can be represented as 2 pi r because it's located at the distance r, and we multiply it by dr. Another way to think about dA is differentiating pi r squared. If we're differentiating it, we get 2 pi r dr. Yes. So we now have to come up with the bottom for what is dy. Well, basically the case is stationary and the tangential speed of the differential area on the object top is omega r. And since the thickness of the gap between the object top and case is t, the velocity gradient will be omega r over t. So since the thickness of the gap between the object top and case is t, which is this is what t is, the velocity gradient will be omega r over t, assuming a linear velocity profile in the gap. And we can assume a linear velocity profile in the gap because it is a small gap. So in this place, if we zoom in closer, we have a linear velocity distribution, which means that it decreases linearly. So it's the most near the place where the frustum is spinning, and it is least at the top. And this is for a small gap approximation. And over here we have thickness of T. So this portion is basically this portion over here, but we zoomed it in. And why it is T is because the largest gradient occurs at the boundaries. So that's why we use the height of T. Because we have the largest change in velocity. We have maximum velocity at the frustum surface and zero velocity at the top. Now what we're going to do is we're going to have to relate this shear stress to torque. But first we're going to have to relate it to shear force first. So let's call shear force equal to torque times area. And in differential terms, a differential shear force is going to be equal to so F shear is equal to torque times area. And basically a differential area is going to be dA, which is 2 pi r dr. So a differential shear force is going to be equal to tau times dA, which is equal to mu times omega r over t times 2 pi r dr. Now, what is torque going to be? Torque is equal to, in general form, a force times an r length. And that r length in this case is going to be this radius over here, since the viscous shear forces are located at distance r from the center. So then we will have torque is equal to, or rather differential torque is equal to R times differential shear force, which is equal to R times mu omega R over T times 2 pi R dr. And we can further simplify this to be um equal to 2 pi mu omega over T uh R cubed dr. Because R is the only thing varying, but the rest are constants. So now we can integrate since we note that this is a differential torque. So thus the total torque or T total over a face is going to be the integral of dt from some initial value of r to r final. Because we're integrating from basically initial value of r, which is about 0, to final value of r. And we're going to do that for both the top and bottom faces. Um, Before we do that, let us write a general equation for the sum of the torques. Because the sum of the torques is going to um, be plugged in over here. It's going to be T total. And what this T total is actually the sum of the torques on the top face, the bottom face, and also on the sides from the viscous shear forces. So T total is going to be equal to T top plus T bottom plus T side. And we're going to use this one in our power. Okay, so now we're going to calculate the torque on the top face. So it's going to be equal to the integral from the initial value of r we're going to take as 0, and it's going to go to r is equal to 4 centimeters. As you see over here, we have a radius of 4 centimeters, 4 centimeters, which is equal to 0.04 meters. So we go from 0 to 0.04 of dt. dt is equal to 2 pi mu omega over t times r cubed dr. And we can pull this out of the integral because it is a constant. So this one is going to be equal to basically 2 pi mu omega over t times r to the power of 4 over 4 evaluated from 0 to 0.04 meters. So we can now plug in the values. So what is mu going to be? Mu is going to be the dynamic viscosity, which is mu is equal to uh 1 times 10 to the negative 3 Pascal second. Or wait, hold on. To the negative 1 Pascal second. From one of my textbook figures. And omega is going to be equal to 100 RPM. So let's convert it to radians. And 100 RPM is going to be equal to times 2 pi radians over 1 rotation, multiply it by 1 minute over 60 seconds. And this will give you that it's equal to 10.47 radians per second. Okay, what is the thickness T going to be? The thickness of the oil on all sides is 1.2 millimeters. So 1.2 millimeters is going to be equal to 1.2 times 10 to the negative 3 meters. Now we plug in all our given information. So it's equal to 2 pi times 1 times 10 to the negative 1 um, times 10.47 over 4 times 1.2 times 10 to the negative 3 and multiplied by 0.04 to the power of 4. Calculating this, we get that it's equal to, so the torque over the top section is 3.5 times 10 to the negative 3, I believe, Newton meter. Let's now calculate for the bottom side. Okay, now it's time to calculate the torque on the bottom face. So the torque on the bottom face is equal to going to be just the same integrand inside, but different bounds. So we're integrating instead from 0 to 2 centimeters, which is equal to 0.02 meters. So 0 to 0.02, and then integrate of 2 pi mu omega over t times r3 dr. And this one is equal to 2 pi mu omega over t times r4 over 4. And evaluated from 0 to 0.02 meters. So we will have 2 pi times 1 times 10 to the negative 1 times 10.47 uh, over 4 times 1.2 times 10 to the negative 3 times 0.02 to the power of 4, and simplifying it will give us 2.19 times 10 to the negative 4 Newton meters. Now let's turn our attention to the sides. So for the sides, we can also do integration. Basically, we have um, this sort of structure, and the surface area is going to be this ring over here, like so. It's going to be this ring over here. And this is going to be ds. And basically, this area is a differential area. It's called dA. So dA is going to be equal to 2 pi r times ds. And r is going to be the distance of this area from the center. So, and it's going to change according to the height. As you see, the radius here is less than the radius here. And now what we have to do is we have to find an expression for ds. And how we can do that? We can focus on this small portion of our structure, or rather on the other side. So focus on this part. And basically we can call this data. And this will be dy. So then ds, which is this over here, will be equal to um, dy over cosine theta. Because ds times cosine theta, ds cosine theta will give us dy. So thus dA, plugging this in for ds, we have that dA is equal to 2 pi r dy over cosine theta. And we can also, in turn, find another expression for cosine theta by considering the overall structure of the frustum. Yeah, so basically we have R2 over here and R1 over here below. And also a height of h. Um, basically, ry, okay, and then if we draw a line over here, this is actually R2 minus R1. So we're trying to find an equation for this line over here. So that line will be equal to ry is equal to R2 minus R1 over h. This is the slope because R2 minus R1 is the x direction and then h is the y direction. And then plus R1. So basically the idea is that we just came out with a relationship over here using theta, and we can come up with another similar relationship on this side using theta as well. So theta will be over here. And basically cosine theta. Wait, sorry. So let's finish up this equation actually first. So this equation is R2 minus R1 over H times Y plus R1. Because when Y is equal to 0, the radius is R1. However, so cosine theta, or rather, this length, which is the hypotenuse times cosine theta, is going to give us H over here, this H value. So we're going to express the hypotenuse as the square root of, using Pythagoras theorem, R2 minus R1 squared. So R2 minus R1 squared, and then plus H squared because H is the Y, and it's equal to H, which is basically this is the hypotenuse times cosine theta is equal to H. And we can thus solve for cosine theta. Cosine theta is equal to H over square root of R2 minus R1 squared plus H squared. And we can now plug this into our equation for dA over here. Thus, dA is equal to 2 pi r dy or 2 pi r times root of R2 minus R1 squared plus H over H dy. And you might ask yourself, this is in terms of y. So how do we get, so what about r over here? Since it needs a relationship with respect to y. And we actually found that relationship over here already. So we're going to use ry in place of r. Again, like we did for the sides, the torque acting on the full surface area of this face is going to be the summation, or let's say dt is going to be equal to the shear force multiplied by the area, which is dA, multiplied by r. So tau r dA, where r is the distance at which the shear force is being applied, and the shear force is going to be applied perpendicular to this face. So the r is going to be the location r. r. Um, yes. So, and basically for tau, we can use what we found earlier, which is omega r um over in this case, what is it going to be? So omega r over t still. So it's going to be equal to tau. What is tau? So tau we found to be um mu omega r over t. So mu omega r over t times r times 2 pi r square root of R2 minus R1 squared plus H over H and dy. And we're going to use Ry for R. So then the integral will actually be equal to the integral of dt. So this will be for the torque on the side. And it's going to be equal to integral from zero to 0.12 because we're in terms of y, so we're in terms of y, so 0 to 0.12 of mu omega over t um mu omega over t times root of r2 minus r1 squared plus h over h multiplied by 2 pi and then r cubed, and it'll actually be ry cubed over, yes, just ry cubed. So yeah. And then dy. So this whole structure is a constant. We can call it C for now. So this is thus equal to um, C times R for, wait, or let's make it more explicit. Ry to the power of 4 over 4. Um, evaluated from 0 to 0.12. So it'll give us equals C times R evaluated as 0.12 to the power of 4 over 4. And R at 0.12 is the radius when Y is 12 centimeters, which is 4 centimeters, which is 0.04 meters. So it's equal to C times 0.04 over 4 to the power of 4 over 4. Oh, oops. And actually, don't make this common mistake. Actually, it's not as simple as that because we have C over 4 and then times R at 0.12 to the power of 4 minus R at 0 to the power of 4. So this one is actually 0. What do we say? It's radius of 4 centimeters, so 0.04 meters to the power of 4, and then radius at 0 is 4 centimeters, so radius is 0.02 meters to the power of 4. And let's calculate C. So C is equal to mu omega times the square root of R2 minus R1 squared plus H times 2 pi over TH. So again we have 0.1 Pascal seconds for mu, 10.47 radians per second for omega, and R2 minus R1 is going to be 0.04 meters minus 0.02 meters, and then H is going to be sorry, this one is actually supposed to be squared because of the Pythagoras theorem. You must have missed that part. Yeah. Yeah, I wrote it here, but I don't know why I didn't carry it over. 0.12 squared and multiplied by 2 pi. And the thickness is going to be 0.0012. And the height is going to be 0.12 meters. So calculating C, we have that C is equal to. So calculating this, we get that it's equal to 5557.698. And what about the portion without the C? So this portion over here, we calculate it to be, let me see, 0.04 to the power of 4 minus 0.02 to the power of 4. divided by 4. So this portion is 6 times 10 to the negative 7. Um, so now we combine these two. So 6 times 10 to the negative 7 times 5,557.698. And we get that it is equal to hmm, a wrong answer. So let me double check. So actually we forgot a crucial point over here. And that is that we have to divide this part over here by R2 minus R1 over H. And this is because of the chain rule. So when you integrate this since R is in terms of Y, if we differentiate it again, we will see that we will get 4RY over 4 and to the power of 3, but we still have DRY with respect to dy. And dry with respect to dy is actually going to be R2 minus R1 over H. So R2 minus R1 over H. So when we are integrating it, we have to make sure to take this into account by dividing by it so that it cancels out and gives us what we have originally. So that is why. And this is important step to remember to do. So our new calculation for this portion is going to be 0.04 to the power of 4 minus 0.02 to the power of 4 over 4 times 0.04 minus 0.02 over 0.12. And this calculated to be, yeah, so this will give us 3.6 times 10 to the negative 6. And calculating it out, basically, we will multiply, so basically t side is equal to 3.6 times 10 to the negative 6 times 5557.698. And this time it gave me the right answer. It's equal to 0.02 Newton meters. So now let's add T total. T total will be equal to the value for T bottom and T top. So it'll be equal to 3.5 times 10 to the negative 3 plus 0.02 plus 2.19 times 10 to the negative 4. And this will give us 0.0237 19 Newton meters. So power, as we said in the at the very beginning, power is equal to torque times the rotational velocity. So power is equal to um T total times rotational velocity, which is equal to 0.0237 0.23719 times what did we say rotational velocity was? So 10.47 radians per second. And it's equal to, oops, okay. 0.248 watts. And this matches indeed our given answer or our expected answer at the beginning. And I hope this video was helpful for you guys. And don't hesitate to reach out with comments. I'm going to be posting these slides afterwards. And have a awesome day.